Good morning, everyone. I'm Simon Chislett-McDonald from Durham University, and I'll be presenting my research on training your tokamak using demountable superconducting coils. I'll briefly discuss the pros and cons of a few superconductors and the necessity for demountable coils before presenting my research about swapping coils during a reactor lifetime. Superconductors are an enabling technology for advancing fusion reactors and future fusion power plants. They have high current densities compared to resistive materials like copper, can produce much larger fields, and significantly reduce the cooling power drain in the reactor, making the production of net electricity much more straightforward. The binary alloy, niobium titanium, is the workhorse superconductor of the world. Its ductility makes it mechanically superior and much easier to manufacture and work with than other superconductors, such as niobium-3 tin and Rebco, and it is also much cheaper. Its downsides are its low upper critical field and low critical temperature, limiting its use to date. Quaternary niobium titanium has additional alloying elements that increases upper critical field, and it currently holds the record for the upper critical field of any niobium titanium alloy. The higher critical field increases its scope for use in fusion reactors. It has, however, never been produced on an industrial scale and only in a few lab samples. Rebco high-temperature superconductors have very large upper critical fields and temperatures. They are being considered for use in next-generation fusion devices such as CFS MIT's Spark reactor. Their downsides are their very high cost of manufacture, innate brittleness, and difficulty in quench detection and mitigation. Moving on from superconductors to tokamak magnets, one of the major flaws with current designs is the lack of accessibility to the magnets once they've been installed, as well as the difficulty in accessing components within the magnet cage. Robot arms and components must fit in the tight space between the TF coils, making the repairs laborious. On top of this, if a magnet were to become damaged and require replacement, an entire section of the tokamak, vacuum vessel, inboard components and all, must be completely removed before the coil can be lifted out in another slow, laborious process. This results in very long downtimes of the orders of months or even upwards of a year. These accessibility issues make fusion power plants unattractive on a commercial level. A power plant cannot risk downtimes of these magnitudes. Future fusion power plants absolutely must be designed with demountable coils that can relatively easily be removed and replaced should the occasion arise. Given that future tokamaks will have these demountable coils, my research has been to investigate a possible avenue for development that this opens up: the ability to swap superconductors in a reactor, combining the benefits of multiple superconductors at a different stage in a tokamak power plant's lifetime. To investigate this, I've used the process systems code. The code uses simple 0 and 1-dimensional engineering and plasma physics models to model fusion reactors of user-defined specifications. It's very capable of yielding first-order reactor designs and is used in the initial step of the EU demo baseline design process, for example. As part of the reactor design process, we've been working in collaboration with the CCFE neutronics team in order to optimize the neutron shield of the reactors that we're studying. That is to optimize the neutron shield thickness, using the minimum amount of shield required to reduce the total magnet heating to 10 kilowatts and full power lifetime to more than 40 years. Swapping magnets presents two scenarios. The first is to use training magnets during the commissioning stage of a reactor. Faults are being ironed out and disruptions are more likely to occur in this time. It will be better to use robust and cheaper niobium titanium magnets than risk damage to full power, perhaps Rebco magnets, before then swapping them in later. The second scenario is the potential to upgrade to higher field magnets as power demand grows. It'll be much cheaper to upgrade a reactor that produces, say, 100 megawatts of electricity to one that produces 500 megawatts of electricity by swapping in more powerful magnets and other components than it would be to build an entirely new reactor. The methodology for testing the two scenarios is simple. Start with a reactor optimized for minimum capital cost with either Rebco or niobium titanium magnets, then fix the reactor geometry based on that and swap the superconductor within the winding packs of the coils, and then re-optimize the reactor for maximum net electricity yield, allowing operating parameters to vary, but keeping the reactor geometry fixed. I've tested 4 different scenarios, 100 and 500 megawatt electricity Rebco-based reactors with combinations of binary and quaternary niobium titanium training coils, and 100 and 500 megawatt electricity binary niobium titanium reactors with combinations of quaternary niobium titanium and Rebco upgrade coils. Using binary niobium titanium TF or CF training coils results in negative net electricity production, though the magnets are able to reach a decent fraction of the full power operating conditions, so it could be viable during commissioning. Quaternary niobium titanium is able to match Rebco at this scale, making it very attractive. At 500 megawatt electricity, the magnets are larger, so require more steel support, reducing the optimal field on the coil. Binary niobi can therefore produce a larger fraction of the full power field. However, in this larger reactor, quaternary niobium titanium can't quite reach full power conditions. Upgrading a 100 megawatt electricity binary niobium titanium reactor with either Rebco or quaternary niobium titanium coils results in a massive 540 or 450% increase in net electricity. Fusion power gains greatly exceed additional power draws, and the upgrade allows for much larger fields produced by the TF and CS coils. At 500 megawatts of electricity, the larger coil radii mean the stresses on the coils are larger, so the possible increases in field are more subdued. That said, swapping the Rebco coils would still produce a 160% increase in the net electricity output of the plant, so there is still scope for upgrading. To conclude, binary niobium titanium training coils would be able to produce a decent fraction of a cost-optimized Rebco Tokamak's operating field. Quaternary niobium titanium would be clearly superior to binary niobium titanium in the TF and CS coils, and upgrading demountable niobi magnets with a 100 megawatt reactor could yield a massive 5 times increase in fusion power. Thank you.
Great. Thanks a lot, Simon. I really appreciate you taking out the time.